Yeah, we're cooking. All right, so we were writing our simulator, and let's see where we left off. What class is this? 350. Okay. So we have our process scheduler. Our process scheduler keeps track of 3 different queues. When we say start a process, it randomly generates a process. Here's our PCB. Did we leave our message to ourselves on what we should do next? CPU maybe? Do next. Make the CPU process multiple instructions. Okay. So we were writing the process method for our CPU. So process is what the CPU does when it's working. Okay? And this guy is going to get called after a context switch in. So whoever is going to do that. Okay? Do we actually write that yet? Start PCB. Yeah, this is it. So we'll either... so it would be this. In our start PCB, it would be this dot process, something along those lines. So we'll come back and call that later, but that's the point in which that would happen, after something enters the CPU. Actually, let me ask you this. So back to our start PCB thing. If the processor is currently not working, that is, there is not a current PCB that it's working on, we're just setting cur PCB equal to that guy. Oh, we say context switch it in. Question I was going to ask, down here, this is the else. That's if the CPU is currently working on something. What do? We context switch what it's currently working on out. Then we context switch what it needs to work on in. My question is do we actually need to context switch in the situation where the CPU is not currently working on something, or can we just set the cur PCB equal to that PCB? So do we actually need to context switch in? Why or why not? Silence.
When you're context switching in, you're setting. You're taking some steps to set up everything.
Yep, here I'll show you context switch in. Here's context switch in.
Yeah, so you can't just set the current PCB to whatever the new one is, because you still have to go and set the registers to the right values.
Okay, but in this particular case, the processor wasn't doing anything. So can we assume that this is the first PCB? Can we assume this is the first time that PCB has entered the system? Kind of like our computer just turned on?
Yeah.
Can we? So if we assume that, do we need to load the registers, or are we starting from scratch? In that situation, it could be. There is no preloaded, we don't have registers to load in. So the idea here is, if we're in this if statement, that means we just turned our computer on and the processor's never worked on something, this particular boot, and a PCB was just born and he's first in line and he's entering the CPU. What kinds of things does the context switch in do? Well, it sets the cur program counter. It copies over the registers. That's what context switch does. Do we, even if it's the first time in, do we still need to set the cur program counter? Yeah, CPU needs to know where it's working, right? Okay, that's the key. That's his starting point for start working through lines of code. We can make an argument whether or not we actually have to set the registers. Does it hurt to copy the registers over the CPU's registers so that they're in the same state as the PCBs are? Even if they're in the initial state, does it hurt anything? Slight little performance bump, but rather be accurate than make an assumption. All right, well, let me ask you this follow-up question. Can you give me an example of a situation where we would be in this if statement, but this is not the first PCB? Or we may actually have a bug in our OS right now because of this. Has to do with how our current context switch in and context switch out works. Right now, well, here, let's start with the punchline. Is it possible, not necessarily probable, but possible, that while our computer's on, while our operating system's running, while the CPU is capable of doing work, that we literally have 0 PCBs in the queue? And the CPU literally has nothing to do. Highly, 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 highly unlikely. Because we know that there's like a bunch of crap running in the background of our operating system that we had nothing to do with. But is it possible? I think we can make the argument that it's certainly not impossible. Certainly not impossible. Therefore, is it, the way we currently have this written, it's not, but we should question whether we currently have this written correctly. Is it possible that a PCB would come onto the system when the current PCB is null, and that not be the very first PCB? And it may also not be the first time this particular PCB has entered the system. Could one of our programs have been waiting for I/O for 20 minutes while the CPU just emptied out? Everything else is closed, everything else is finished, the processor is completely done. It's just sitting there doing nothing. Finally, an old PCB that maybe has already gone onto the CPU 30 times finishes its I/O request because the user didn't click the OK button. On the Mac, it's when you got the little icon that's jumping up and down or somewhere. Any of you find that annoying?
Yes.
It's like, it definitely works to get your attention, right? But at what point is it, can't decide if it's good or bad. For Microsoft, they kind of did away with it back when they had that paperclip dude.
Clippy.
Yeah, remember that? Remember that guy? They should have made a, I don't know, like some kind of cartoon around him. Like an Adult Swim. All right. So it is possible that a PCB could be stuck in the I/O queue for 20 minutes. Let's just use human time. That means something to us. For 20 minutes, and the processor becomes completely emptied out. It's not currently working on a PCB. Now, as we have it written right now, we never actually set a PCB to null. So when something context switches out, we probably want to set cur PCB to null. Effectively saying, I've stored you, now get lost. So I forget about you up on the CPU. Then when the context switch in guy comes, part of it is set the cur PCB to that guy, set the cur program counter to that guy's thing, fill in the registers. So context switching in makes the CPU aware of the cur guy. Context switching out makes the CPU forget about the cur guy. That makes sense? That way we're always dealing with, that way we have the possibility of having a cur PCB set equal to null. Because what we could have is if the CPU emptied out, as we currently have this written, the very last PCB that was on the system is still being remembered by the CPU. He's the last dude I worked on. That makes sense? So we actually can create this scenario. We go to our context switching. So context switching out says this dot cur PCB is equal to null when we're done. So I did all the crap to store this. Now I'll forget about it. Context switching in says I'll do all the crap to load him onto the processor. Now let's set him as the guy I'm currently working on. Make sense? which means now when we go down to start PCB, we would never set the cur PCB equal to the PCB here. Instead, if cur PCB is null, that means we don't need to context switch out. Correct? We can skip the context switch out part. So we can do this dot context switch in the PCB. Here, I'll actually put it after my comment, just so things make a little more sense. All right, CPU is not currently busy. Let's just context switch in the dude. If the CPU was currently busy, we need to context switch out the dude first, then context switch in the dude. All right, regardless of what happens after we've context, in either of these cases, something's been context switched in, right? So in either of these cases, something's been context switched in. So we know the CPU is ready to work. How do we work? This dot process. CPU processes the cur PCB. Okay? So let's go back to our process method now. So let's look at what we currently have written in here. Let me minimize this side, show us a little more code. So we'll get our current instruction. So that's the cur program counter. So the CPU knows about the current program counter. We'll ask the PCB for that particular instruction. We wrote that last time. So here's in PCB. We have get instruction, which takes in a pause, and we're not checking to make sure it's legal. We'll do that later. But right now, it just returns the instruction at that pause. Okay, remember our instructions are either an IO instruction or one of two move instructions, literal or register moves. All right. CPU. Okay, so we'll get the next instruction. Then we'll increment our cur program counter so that the next time we request an instruction will be the next one. Now we're going to parse the instruction. So if it's an IO instruction, then we're going to do IO crap. We'll decide what that means. Else, it must be a move instruction. So we'll split it on the comma. We know, so here's the examples of what it could be. So bucket 0 could be like move :2. Bucket 1 could be lit :5 or reg :1, something like that. Then we'll get the left part, split that on a colon. So that gets us bucket 0 as a move, bucket 1 as a 2. We'll get the right parts, split it on the colon. Bucket 0 would be lit or reg. Bucket 1 would be 5 or 1 in this example. All right, then we'll get our destination index. This is where we're going to put it. So that is the left parts. Actually, that's not, yeah, that is right. Okay, the destination index is this guy right here. Yes, so that's the register at bucket 2 in our register array. So where are we putting it? We're putting it at, in this example, would be bucket 2, if this is what it looked like. And we're getting that integer, so we can use it. If the right parts at bucket 0 is a lit, that means we're looking at something that looks like this. We're just going to load, in this example, 5 into bucket 2 of our registers. That's register 2, whatever that is. So we'll say the registers at position destination index is equal to the integer version of the right parts at bucket 1. So in this example, that's a 5. Else, the registers at bucket destination index, same destination, is equal to whatever's currently in the registers at bucket integer.parseInt, whatever. So that's copying from one register into another register. All right, so in this else, we are executing the move instruction, 2 different versions of it. After this is done, after this else is done, what do we want to do next? We just processed an instruction, right? Well, we haven't written the IO part, but we know what happens with the IO part is we're going to move this guy into, he's going to context switch out and go into the IO queue. We'll deal with that later. For right now, let's just assume all instructions are move instructions. So I'm the CPU. I was told to process. I came and grabbed the first instruction, and I processed that instruction by moving the values around into the appropriate registers. Okay? So from our perspective, what happens right now is that the values in our registers changes. That's all that our mini computer knows how to do. Move crap around in registers. Okay? So after this else is complete, we have finished that move instruction. What should the CPU do next? Remember, we're the CPU right now. That's the object we're in. So put ourselves in the CPU's shoes. If we're the CPU, we are this. That's what we are, this instance of the CPU. So I just finished executing, processing a move instruction on the current PCB. What should I do next? Next instruction. So I should loop back up. Call process. Get the next instruction. Increment program counter. So should I call it recursively? I could. Certainly could call it recursively. Is it dangerous to call it recursively?
Yeah.
Okay, why?
Because you could run out of memory. You have a lot of instructions.
Okay, is it likely we're going to have a lot of instructions?
Probably not.
Hmm.
With our setup, with one of them possibly being an I/O every quarter.
Oh, I understand what you're saying. Situationally, in our situation, we probably wouldn't have a problem. But if we expand that to generalistic operating systems, we're going to be dealing with millions of instructions. So certainly could become a problem. But to take it even a step further, dealing with recursion. And this almost becomes the litmus test as to whether or not you should use recursion in certain situations. If we were to make a recursive call, let me just do it right now. So I'm just going to say this dot process. Process another instruction, right? That's what this would say. Process this instruction right here. After we're done, what do we do next? Go on to the next instruction. How do we process an instruction? Well, we call process. That's what we do. So here's the litmus test. If I recursively call this method from within itself, so I'm calling process from within itself, the current version of process needs to be put on hold. Okay? It cannot complete until all future calls to process have finished. Now, is there any reason, since we know what this code does, is there any reason for the current copy of process to still exist? We've finished, right? There's nothing in here that we're going to have to come back to. When you think about our first recursion example that you learned back in 250, that first recursion example dealt with something like factorial, right? I actually find this kind of fascinating how classes overlap. Because I'm teaching 250 right now, and we're talking about recursion right now. In fact, we just talked about, I think, factorial 2 classes ago. Interesting. In any case, we talked about that, like 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial, so on and so forth. The previous call to the method was reliant. It could not finish until the next call to that method. 4 factorial could not finish until 3 factorial was solved. 3 factorial could not finish until 2 factorial was solved, so on and so forth. That's a perfect example of when recursion maybe does make sense, assuming memory isn't going to be an issue. Memory's always got to be our first, our first litmus test. It's like, yeah, recursion's elegant, but I'd rather our program work than crash out in the middle. But in this case, putting this guy on hold is a waste of time, waste of memory. He's not reliant. This particular call to process is not reliant on the next call to process finishing. This guy can end right now. Correct? So the question is, how do you implement? How do you implement this? Well, we can throw it in a loop, right? So let's kind of evolve through this until we get to a reasonable solution. So our next solution is still going to be bad, but you can tell me why it's bad once we write it. So we're not going to recursively call this .process. We want to do the same crap again, but we can repeat stuff by using loops, which is much more memory efficient, right? So let's just put this entire thing inside of a loop. So that's what we're doing here. Make the CPU process multiple instructions. So for right now, just to so we don't have to worry about our Boolean expression, we're just going to say while true. Do all this crap. We're not going to keep it as while true. Well, we might, but certainly we're not going to have this be an infinite loop for real. At some point, we're going to have to do some context switching. But for right now, we're just going to say, look, keep processing crap until further notice. That's what this loop says. Okay? So forever, we're going to get the current instruction, increment the program counter, determine what kind of instruction it is, process, 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 rinse, lather, repeat. Make sense? All right. Now, if we do it this way, so this becomes, I don't want to give it away yet. I want to see how smart you guys are. My expectations are low, especially. You know, I actually used you as an example at a Bible study this weekend.
I don't know if that's a compliment or not.
It sort of is.
Oh, really?
Yeah, it sort of is. We were at a dinner with it was like, it's called Upper Room at our church. So we were at dinner with our pastor and his wife and a couple other members of the church and me and my wife, and so 7 people. We had dinner and then we have a Bible study afterwards. And we were talking about different things. I don't even remember what the context of it was, but I used the example from a couple weeks ago where for a couple years now, I always give you a hard time about random stuff, and it never upsets you. But when I gave you a hard time about an academic thing, it ticked you off. And that bugged me, because I didn't recognize that. So I found it interesting. And then I just did it again. But I did use that as an example. Yeah, so for everybody in here, when I make fun of you, it's out of fun, not because I really think you're stupid. But so I usually only pick on people that have shown that they would find that entertaining. I'm still working on him, though. I did get him to, actually, you got him to laugh. All right, so in any case, what's this? That's right, yeah. It was, if you need a reminder, it was. All right, I also told that story at Bible study. So evidence is I'm the same way in class as I am at my pastor's house, is what I'm saying.
So if I manage to get to church next weekend, am I going to get like a talking to
By?
the pastor?
I don't know if I said it was you. Actually, I did say it was you. I'm pretty sure I said it was you.
We have to ask you not come to this church.
You know Hillenbrand pretty well, don't you? Hillenbrand's he's a very good pastor. He's cool. He would never do that stuff, but he gets it. He gets it. We're very lucky to have him at the church. At least I am, because I would be ostracized. Otherwise, it would be probably problematic.
You yelled at him to get a Mac in service one time.
That's true.
Right. It is really
That's true.
bad.
Yeah, see? Like I said, you guys don't just get it in here. I do that in the middle of church. Same stuff.
While playing golf.
That's true. Yeah. But now I can't use that as an excuse. It literally snowed this Sunday. Oh my gosh.
Yeah,
Huh?
I have never been here when it has snowed before Thanksgiving.
Really? I think we have. Well, it's got to be worse for you. How long ago did you live? You were in San Francisco?
I was in San Francisco
Yeah.
5 years ago.
Oh, that's got to be just depressing.
Oh, it is so depressing.
I
So depressing.
mean, a lot of people like Wisconsin, but I'm a golfer. That's kind of like the idea of San Francisco. It's kind of what I'm saying. So if we didn't have cats, I'm just saying. I don't know what I'm saying, but I'm saying. I don't think my wife would want to move out there. So if I wasn't married and we didn't have cats, so now I'm just trapped. Trapped in Wisconsin. All right, so each time through, we're going to keep processing. Now, we're inside of an infinite loop here. When we want to stop processing, well, let's go this route. When do we want to stop processing? So this gets back to our idea of interrupts, right? So way back when we first started talking about process scheduling, we were talking about interrupts. So the CPU just does its job, okay? It's got tunnel vision. I'm just going to keep working on this current PCB until somebody interrupts me and tells me otherwise, okay? Or I interrupt myself when I run into some gristle that is an I/O instruction, something that I can't work on, okay? So externally, if I'm the CPU and I'm just working away, somebody needs to be in charge of me. Somebody needs to tell me when it's no longer time for me to work on this current PCB. So we just talked about one possibility, that's an I/O request where the CPU updates itself, then goes back to the process scheduler and says, I need more. Okay, so that's one example. The other example is the CPU has used its time on this particular PCB. Okay, now who keeps track of that? As part of the operating system, we have a CPU scheduler. All right, so CPU scheduler, process scheduler, and the CPU itself, and really memory, work very, very closely, which shouldn't be surprising because we consider operating systems, even though they're complex critters, we can imagine that the different parts of an operating system work very closely, right? And they're all interrelated. So even though we just basically listed 2/3 of the entire operating system's important parts all working closely together for this one piece, that central processing unit is kind of an important part of computers working. Okay, so the CPU scheduler is going to keep track of how long the CPU should work on something. So before we actually write it, let's just talk about it at the high level. So let's say that I'm the CPU, and Abe, you're the CPU scheduler. So you're the slave master. Okay. So, wait a minute. I was about to go with the Princess Leia outfit thing.
Your job of the hut now?
No, wouldn't that be him?
You fit the size ratio better.
All right, fine. I'm Jabba the Hutt, you're Princess Leia. I kind of regret not switching that over to Evan and having his new nickname be Leia. But I'm really concerned my tires would get slashed. All right, so in any case, okay, I'm the CPU and I'm just chugging away working on the PCB. Whatever the Cur PCB is, whatever this guy is, that's my job, okay? One track mind. I'm just going to process instructions from the current PCB, Cur PCB. If that changes, no problem. Next time through, when I ask the Cur PCB to give me its instruction, it'll give me the instruction from the Cur PCB. The hope is there's been a context switch before that happens so that I'm asking for the correct instruction. That make sense? All right, so in any case, as the CPU scheduler, let's just use the use human time. So let's say I get to work on a process for 3 seconds. I can accomplish a lot in 3 seconds as a CPU. I'm you know, we can do lots of instructions per second. Okay, so for 3 seconds, I get to work on the current process. In fact, 3 seconds would probably be an unreasonably high number for operating systems, but we can work with 3 seconds. So after 3 seconds, Abe's going to come to me and say, okay, you're done. He's going to interrupt me and say, when you complete the current instruction, you're interrupting me?
No, I was going to ask if I can come in with the whip.
I'm cool with that. I wonder if the microphone picked that up. So in any case, after 3 seconds, you're going to interrupt me, at which point I'm probably going to finish the current instruction I'm working on, because it probably adds a whole nother layer of complexity if we need to roll back to the previous instruction. Might as well just finish the instruction, right? Okay, so CPU gets interrupt me, so you basically like, you interrupt me. I finish what I'm currently working on, context switch that out, then you, working in conjunction with the process scheduler, are going to context switch something in. Okay, so the process scheduler goes to, well, actually, let's think about this. Let me draw a picture here. CPU schedule. All right, so we have the CPU scheduler. We have the process scheduler. We have the physical CPU.
There's a button to go in the center.
Really? Where? Teach me.
Just under, middle one.
This guy?
I think so.
So then I need to take out my spaces. Ha-ha! Star for the day. You should see my expertise with Photoshop. Surprisingly mediocre, but I can usually actually make things pretty cool.
So what you're saying is next time expect a Photoshop picture of Slave Leah with
Right. Brought to you by Amish. It's going to be whittled out of a tree stump. All right. So we have the CPU. This is the resource we're controlling. The CPU scheduler handles when things come in and out of the CPU. So the only dude that talks directly to the CPU is the CPU scheduler or the CPU itself. We can decide, since the CPU is actually a piece of hardware, if that comes as a surprise to you, since it's actually a piece of hardware, more than likely the way the software might be written is that when the CPU hits an I/O instruction, what would happen is the CPU would request that the CPU scheduler interrupt it to kind of keep the algorithm the same. So it's the CPU scheduler that always does the interruption. All right, so CPU scheduler. Has an interrupt request. IRQ is one of the short things for that. That's when things context switch in, context switch out. The CPU scheduler also works in conjunction with the process scheduler. So the process scheduler is the CPU scheduler source for PCBs. All right, so this is the honeypot, if you will. So the CPU scheduler comes and grabs a PCB from the process scheduler, and the process scheduler is always going to feed PCBs out of what? So our process scheduler out of its ready queue. Does that make sense? Always going to feed things out of its ready queue. So CPU scheduler says, I need the next PCB. CPU scheduler grabs that PCB. Now it has it on hand. It's probably done this before it's interrupted the CPU. You want to have that transition to be as quick as possible. So the CPU scheduler says, I need the next PCB. Then it's going to interrupt the CPU. Interrupting the CPU says to do what? Context switch out, and then context switch in the next guy. Now go. Okay? So in this situation here, this is, that's Abe. How do you spell Leia? That's it. Parentheses. All right, so that's Abe and Leia.
I thought I was Leia.
I don't remember now. But I think this is a biblical worldview, a Christian worldview. Because Abe, short for Abraham, he's in the Bible.
You saying that Abe is a biblical worldview incarnate?
Yes, in a box, in a circle. It's a circle.
So it's just
And the circle's in a box.
So it's more or less.
All right, shut up. I want to get through this. All right, so I'm chugging away on the current PCB. Abe's going to request from the process scheduler. Okay, so we're organized person. So Angela's going to keep the list of all the PCBs currently in the system. Abe's going to say, okay, I need the next PCB. He's going to get that PCB. Then he's going to interrupt me. When he interrupts me, he's going to tell me to do a context switch out. Then he'll tell me to context switch in the PCB he just got from Angela. Then he tells me to go again. Okay? So he stopped me by interrupting me. Now he needs to start me by telling me to go again, to start processing again. Now when we go back to our code here, as the CPU, we currently have our process just stuck in a big loop. Okay? So we could maybe have this attached to a global variable, maybe called ShouldProcess, something like that. So maybe at the top here we have a private Boolean ShouldProcess. And this guy will start off as false. Initially we should not process. Okay, then we're going to have a public void set ShouldProcess. And this isn't going to be the way it's going to stay. I'm just going down this path to show you something that's kind of a problem. Okay, so now we'll give an accessor method for our set ShouldProcess. And we're going to process as long as this dot ShouldProcess is true. So as long as this is true, we're going to keep processing. When it's not true, this particular loop through process stops. Okay? So that's our current setup. So I'm going to, every single time through, I'm going to check this little variable. You know, does ShouldProcess say I should keep going? Does ShouldProcess say I should keep going? Does ShouldProcess say I should keep going? So on and so forth. And I'm going to do my processing thing. Okay? Now, ideally, Abe comes in and interrupts me. Why can't that happen right now? From a programming perspective.
There's never time for him to come in and interrupt.
Okay. Tell me more about that.
Because you just keep looping through and there's no reference to the CPU scheduler. There's no reference to the CPU scheduler to give him time to actually set anything.
Okay, so this is our CPU that currently has our loop in it, right? So once we start processing, we're going to keep processing as long as ShouldProcess is true. Ideally, the way Abe is going to interrupt the CPU is by setting ShouldProcess equal to false, which will make me not process another instruction, right? I'll automatically finish the current one I'm on because that all happens within the loop, but I won't start another one. I'll fall out of that. That's how he can interrupt me. Oh, what's wrong with that? So in a real life scenario, I can be sitting here working away, and all of a sudden Abe could just say, wait a minute, set my ShouldProcess to false. So I finish what I'm doing, and now I look up and wait for instructions. Why can't that happen in our program right now? There is something, where's my CPU? This loop keeps us from being able to do that. The question is why? Specifically why? This code right here is said to do what's called block. As long as that loop is running, nothing else related to this program can happen. All the process control is currently here. This is what we're doing. Whenever we finish doing this, we can go back to whoever called this. But while I'm in here spinning around, Abe doesn't get to work. He doesn't get to do his thing about interrupting the CPU. Okay, because I'm blocking. Once he tells me to go, he doesn't get 2 words in, or even 1 word in. He's on hold until I finish. And the problem is nobody's going to tell me to finish because he can't do his job. What's our solution for that? This is actually historically, it goes back to how operating systems initially evolved. In our early operating systems, they were single programmed operating systems. They could run 1 program at a time. We couldn't run multiple programs. Why not? That's why we have threads. And that's why we created the fork system call. So what we really need to do is we really need to have the CPU scheduler, Abe, operating in his own thread of execution. The CPU itself operating in its own thread of execution. And this just mimics real life. So if I'm the CPU and Abe's the CPU scheduler, just like in real life, what Abe does throughout the day as a human being has no impact in general on what I do throughout the day as a human being. We both can act independently. Sometimes we come together and can give instructions. Okay, so that interaction can happen, but otherwise we can both do our own thing. So each of us would be operating in our own thread of execution. All right, so when we create the CPU scheduler, that needs to be done in a thread. When we create the CPU is an instance of a CPU. It needs to also be in its own thread. You can make the argument that the process scheduler should also be in its own thread. All these individual pieces need to be able to do their thing themselves and then interact when it makes sense. Okay? But we need that process scheduler, so if we go farther back on the line, while the CPU is working and the CPU scheduler is doing its thing with the CPU, the process scheduler still needs to be able to support new processes being born. PCBs going into memory, actually getting created, getting put into the jobs queue, getting put into the ready queue or the IO queue. It needs to be able to do all that without having to interrupt the CPU or the CPU scheduler. Those things all need to happen at the same time. That makes sense? Realistically, if you're writing this at the operating system level, and this is kind of why C is a good language for operating system design, you probably would implement this as a fork. You fork separate full processes that get their own CPU time. as opposed to having all this happen within a single thread, which then can actually compound performance issues because they're all sharing CPU time of one thing. We're probably okay with our operating system monopolizing more of the CPU than our instant messenger. Make sense? All right, so we'll come back on Wednesday and we'll keep going, and hopefully I can give you your next homework assignment on Wednesday. It's going to be a doozy. I should give you a quiz on Wednesday too. We're overdue. All right, see everybody then.